recording. It is recording. Question 4. The network represents a system of pipes through which oil can flow. The weights on the arc show the capacity for the pipes in litres per second. Explain how you know that the source is an F and identify the sink. Well, it's telling us that the source is an F. What is it that stands out about vertex F? There it is. Well, that's the only one, isn't it, where the flow is out and there's no flow in. So we know that F is the source because the flow is only going out, not coming in. So we're looking for a sink where flow is only going in and no flow is going out. And so as we kind of look through all of these ones have an arrow coming out of them. There we are. J is the only one that has flow in and no flow out. So the source is F. Only flow out, none in. What is going on? And the sink, we've just said was J because it only has flow into it, but you didn't have to say why. Right, part 2. Calculate the capacity of the cut that separates A, B, C, D, E, F from G, H, I, J, K, L. So the cut that we're looking at, A, B, C, D, E, F, separated from G, H, I, J, K, G, H, I, J, K, L. Okay, we're looking at things that are flowing across the cut. Well, actually, they're all flowing across the cut, aren't they? Because they're all flowing from the F side of the cut to the J side. That's F to I is there, E to H, E to H is across the cut, D to G, D to G is across the cut. So all 3 of those are flowing across the cut. So we're adding them together. So the cut is, what did we just say, 8 plus 10 plus 12. So there's a cut there of 30. Great, another very straightforward mark. Explain why, in any feasible flow, pipe BA cannot be at its full capacity. Explain why the flow in pipe FC cannot exceed 15. So again, we probably need to look at this, don't we? In any feasible flow, why BA cannot be at its full capacity. So BA is that one. And why the flow in pipe FC cannot exceed 15. So there's FC. Right. Well, what about BA? Let's think about that to start with. Its full capacity is 6, flowing into A. If the full capacity of 6 is flowing into A, but we can only have a maximum of 5 flowing out of A. So that would exceed the amount that could flow through A. We have stuff going in, but couldn't have any way out. So we're stuck on that one. At most 5 flows out of A. Along AD, and so therefore you can't have more than 5 flowing in. So not 6. Okay, so that's the first bit. What about FC? Explain why flow in pipe FC cannot exceed 15 litres per second. Well, that's a bit more complicated now, isn't it? Because now what we're saying is that the true capacity of BA is 5. So there's at most 15 flowing out of B. So at most 15 can flow into B. The only way into B is from CB. The only way into CB is from FC. So that path there has to be at most 15. Otherwise, we wouldn't have anywhere for it to go when it got to B. Does that make sense? So how can we put that down? So BA, we said, has a maximum of 5. BE, at most 10. So that is 15 at most flow into B. Along CB, wasn't it? Is that the one? Yeah, along CB. And if at most 15 flow along CB, that flow must have come along FC. Comes from FC, so FC is at most 15. And there we go, that's that bit, and so it's quite nice. Right, go on to part 4. Show a flow through the system in which the flows in pipes FC, IL and KJ are as large as possible, and nothing flows in pipes ED, FE and IH. Right, so we've got this diagram to fill in. Let's start by putting in as much of the information as we can from the diagram, from the question. It says, nothing flows in pipes ED, FE, and IH. There. Okay. Now we've got to think. We want the flow to be the most that it could possibly be. Now we've just talked about the whole idea that we can have 15 flowing along FC and BC and then flowing out to those ones. So let's start off by seeing if we can run that round. So let's put our 15 in there. That was one of the ones we had to have as large as possible. So that makes 15 in there, if 15 is flowing along that path. That involves 10 flowing along there and 5 along there. So 5 is along there as well. So now let's see if we can follow everything else about what's going on with this. We've got 10 flowing along that path into there. So it must all be flowing out because there's none going along that road. So that must be 10. We've got 5 flowing along there, so there must be 5 flowing along there. We've now got to make some more decisions, haven't we? Because we've now got to decide how many are we going to allow to flow along FI. We were told that IL had to be as large as it possibly could be. Well, actually, if you look at the diagram for IL, it's way back here, IL is 6, but LK is 4. So actually, the most that could possibly be is 4, if that one is limited to 4. So let's try putting that in. That's 4 there and 4 there. So we need to have 4 flowing into there. That's the most that could be. We've got nothing going out that way, so we have to have 4 going that way. Now it looks like we've got a total flow in the system of 19, haven't we? Because that cut was a kind of good point to look at this. That separates the source from the sink. So we've got 19 total. Right. We've got 4 flowing in there. We just need to direct the rest of our 19 to the end. And at this point, I think, we also had, didn't we, KJ had to be as large as possible. And KJ has a capacity of 13. So we've got to think, is it possible to get 13 through KJ? Well, if I have 9, can I have 9 going in there? I think I can, can't I? There's 9 going in there with that 4, that gives me 13 at that point. Now if 9's going on there, one of those 10 has to go up there, and that's alright because that has a capacity of 4. This has a capacity of 7, and I've got 6 flowing along it, and that's my 19 flowing into J, and my 19 flowing out of F. And so as long as I put something on every arc, that looks like that's consistent. Where some of us fell down on this question was I think we missed the bit where it said KJ has to be as large as possible. So it was quite common for people to have flows that were 19 through the network, but had just directed all of those 10. I can't remember how you've done it to not get that. You had more going up there, and that one was bigger, and that one wasn't at its maximum. That was where it fell down. Okay, it doesn't feel very good doing that, does it? Because it's kind of, you're not really following an algorithm. You're just kind of shoving stuff through some pipes and hoping that it doesn't get stuck. And it doesn't feel that great. Now we actually get to use the algorithm though, because it says, using your flows from part 4, label the errors in the diagram in the answer book to show the excess capacities and the potential backflows. Write down the flow augmenting path, but do not update the excess capacities. Hence state the maximum flow through the system. And write down the cut that shows that this flow is maximum. Right, so we've got to convert what we've got on that diagram onto this diagram. Oh, I've got my... Oh, we'll cope with it. Right, so let's start doing it. We have to refer back to the original network diagram here as well, don't we? So that we know how much our excess is. So let's start from F, which was the source. We have 0 going along it. So we can increase it by 5 and reduce it by 0. We have 15 flowing along this one. So we can increase that by 5 and reduce it by 15. Here we have 15 flowing on this one, so we can reduce that by 15, and its capacity was 18, so we can increase it by 3. This was 6, so we can increase it by 1 and reduce it by 5. This was 5, we can increase it by 0, reduce it by 5. This arc here was 10, so we've got no that we can increase, and 10 and we can reduce it. We've got 0 going on that one, we can increase by 2. We've got 5 along that one, we can increase it by 3. We have 10 along that one, so we can increase it by 0. We've got 4 along here, so we can increase it by 8, because it has a capacity of 12. Where are we then? This arc, we've got 1 going along it, so we can reduce by 1 and increase by 3. We've got none on that one, reduce by 0 and increase by 3. We've got 4 going on there, we can increase it by 2 and reduce it by 4. That one we have 4, so we can increase by 0 and reduce by 4. This was a 9, so we can increase it by 3. This was a 6, we can increase it by 1. And this arc was at capacity, so we can increase it by 0 and reduce it by 13. And that is our fully augmented diagram, fully labelled diagram. We now need to decide if we've got any flow augmenting paths. Is there any way that we can increase things through there? So remember we're going from F. F is the source and J is the sink. How could we do this? Well, we've got, let's make that a little bit bigger. It looks like, well, we can't go up that way, so we have to be going in there. There's only one that we can get in further. Okay. Is there a path that we can take 1 from there? Well, it looks like that would work, wouldn't it? That's one possible path. So if we went F, oh dear. If we went F, E, D, G, J, that would do it. We've got 1 that we can augment that 5 plus 1. So that gives us our 19 that we had previously, plus 1 is 20. And remember that when it comes to the cut, the thing that we're looking for here is, can we find arcs that would be at capacity under our cut? Now, you weren't supposed to augment this, but just kind of thinking this through. Already at capacity, we have that one and that one. What else is at capacity? That's at capacity, isn't it? That's at capacity. Now, if we do our flow of 1 going through it, it makes that one at capacity as well. And that would be it. They would be the only ones, I think, that are at capacity if we do that. Oh, there's one more, sorry. That one would be, wouldn't it? So can we think of a cut now that separates the source from the sink? Should have done these a different colour, the source from the sink. Can we separate those going only through arcs that are at capacity? I think we can, can't we? If we were to do a cut, oh, not that one, that went like that, then that looks like that. That does it, that solves the problem. So we need to write down what that cut is. That cut is A, B, C, D, E, F, G, H, I, separated from J. And then to calculate the capacity of the cut, you don't look at this diagram. You go back to the original diagram, separating all of the others from J is a cut of 20. And there it is. That confirms that our flow is the maximum. Therefore, 20 is the maximum flow. And there we have it. Right, there we go. And that's maths. And this, as D2 tends to do, is taking a long time.